be looking at equilibrium. We know that chemical reactions can proceed in either direction. Usually we're looking at the forward direction where we have reactants turning into products, but we know that products can also convert back into reactants. So here I have two beakers. The beaker on your left represents the reactants, and right now it is full, and the beaker on the right represents the products, and right now it's empty. So as the reaction starts, we have all reactants and no products. And as the reaction starts, I have some reactants turning into products, but right at the very beginning, there were no products to turn back into reactants. But once the reaction has started, I now have reactants turning into products, and I do have some products that can turn back into reactants. And as the reaction continues, you can see with each scoop, I'm getting a little bit more in the product, or from the product container. And as I do this, the amount of my reactants are decreasing, and the amount of my products are increasing. But what is the level going to be when they stop changing? At this point, you can see I'm getting almost an equal amount in each beaker. So as the reactants are turning into products, I have an equal amount of products turning back into reactants. So if I were to keep going with this forever, the amount of reactants and products that I have here shouldn't be changing, because every time I scoop, I'm getting a beaker full of reactants turning into products and a beaker full of products turning into reactants. So this reaction would be said to be at equilibrium. Notice that at equilibrium, I do not have equal amounts of reactants and products. What I have is equal rates for the forward and the reverse reaction. The rate at which reactants are turning into products is equal to the rate at which products are turning into reactants. So that means that the amount, or the concentration, of reactant and the amount of the product will be constant. It shouldn't change from here on out. Now, this demonstration isn't perfect for a couple of reasons. One of which is you can probably see that I'm spilling water on the table as we're doing this. But even if I wasn't spilling, the amounts wouldn't stay exactly the same forever, because some water is evaporating into the air. Also, my fingers are kind of getting into the beakers a little bit, and I might not be able to get exactly equal scoops each time. So this isn't perfect for a demonstration of equilibrium, but it is giving you a visual of the amounts of reactants and products do not need to be the same, but they will be constant once it's reached equilibrium. And that's because the rate of the forward and the reverse reaction will be equal. Now, chemical reactions can reach equilibrium, and we'll be looking at those a lot, but physical reactions, or physical processes, can as well. You might remember talking about saturated solutions earlier in the year. And I had this container of salt water that still has some salt sitting on the bottom. And I told you that this salt water has been in this bottle for a few years. And if any more could dissolve, it would have dissolved by now. So we know that this solution is a saturated solution of sodium chloride. But to say that none is dissolving anymore isn't entirely accurate. Some of this is actually dissolving, but at an equal rate, it's precipitating out of the solution. So I have a constant concentration of sodium chloride in the water, but the individual ions, some are dissolving and some are undissolving at an equal rate. The same thing can be true with phase changes. If I have water at 0 degrees, a mixture of liquid and solid, if I'm not adding or taking away heat to make that melting or freezing process take place, I'm going to end up with a constant amount of ice and a constant amount of liquid water, but some of the ice is melting, but an equal amount is freezing at the same time. All right, so what you need to remember is at equilibrium, the rates of your forward and your reverse processes will always be equal, and your concentrations will be constant. I would strongly suggest avoiding using the word same, because we could use that word to kind of talk about either of these. Equal are the same. The rates of the forward and reverse reactions are the same. They are equal. The amount of reactants and products are staying the same. They're staying constant, but they are not the same. So again, if you stick with the words equal and constant or not changing and avoid using that word same, you're less likely to slip up and say something you don't really mean.